So good afternoon and welcome to the lecture today. We're in week 6. You had the midterm last week. I'm not going to say a lot about that at this moment in time. The marking is in progress. Maybe you've already got your results, otherwise you will get it soon. And you will be able to see how you did and the comments that your tutor had when he marked your work. So that's going to be there soon, and I hope you did well. In the meantime, week 6, so we have 2 weeks more of lectures introducing new material. That's going to be this week about integration, which is kind of the reverse of differentiation, as you have already seen in high school. And then there is also week 7, and week 7 we'll be talking a little bit about differential equations and how to solve them. Week 8 is special in the sense that in principle we do not do new mathematics anymore. So maybe if I'm running out of time and I need a bit of extra time, I might use our meetings in week 8 for that. But otherwise it's all meant for exam preparation. So you can already think of what you would like me to do there. So I'll happily discuss any problem you may have during week 8. And if you have questions or a certain topic, or you would like me to do more examples about a certain topic, please feel free to let me know. And you can do that either by email or you can use the question box on Canvas. And talking about that, let's first address the questions that popped up there. There weren't that many this week. I think most of you were focused on the midterm, at least I hope so. So let's see what we have on the website. And I'm going to be starting at the bottom here. So that's a question by Irina. And she asks for a little help on questions 8, B, and C from section 3.1. And in fact, the question above that is related to that. So the question above that is from Anonymous. And that's also about linear approximation. So both of these are about linear approximation. And there is here a complicated question from the online quiz. Now, before I go into that, so both this question and Irina's question, which concerns questions from the book, let's have a short look at what we did last week. So the relevant topic there that concerns this. So let me go to my iPad screen, that's here. So what we were talking about back then is linear approximation. Basically, if you have a function, so the red function here, y is f of x, can be anything. So here I just drew some function y is f of x, and it's the red curve that you see here. Then we have seen that locally, so close to a point P, say, with x coordinate x0. And because it's on the graph, it has y coordinate fx0. So in the neighborhood of P, the tangent line to the graph, so the black line that you see here is the tangent line to the graph. That is a pretty good approximation. So if you stay close to P, if you look for x values that are near this x0 value here, then the linear approximation, the black line, is a pretty good approximation of the function. And sometimes that can help you if you have a complicated function to find an easy approximation of function values nearby. So here in the box is the formula, and that may look a bit complicated, but it's just a tangent line. So if you know how to find the tangent line, you know the slope is f prime, and then you know that this point P, x0, fx0 should be on the line, and that is sufficient information to find the tangent line. So last week we looked at how you can do that. So if you have a function like here, we have the function cubic root of x, and we have seen how you can, close to x equals 8, you can find approximations there. For instance, for 8.02, if you compute what the linear approximation is, then we have seen last week that the linear approximation, so that's the tangent line evaluated at 8.02, gives something that is pretty close to the real value. Now, the two questions that we have online are along this. So if I go back now to the questions, they were here, then so the top question that we have here, the online, you see that this is very, very near what I was just showing you, the slide that I just showed you from last week. So here it is being asked to have the function, and f of x is now 1 over and then the cubic root of x. And then at the point x equals 27, you know the value there, right? You know the exact value, because the cubic root of 27, that's 3, because 3 times 3 times 3, that's 27. And then if you would evaluate the function not at 27 but at 28, that's quite close, you could use a tangent line at x equals 27 to find an approximation. So that's what you should do here, okay? Then Irina's question is a bit more difficult because the book doesn't tell you where you should draw the tangent line, so which x0 you should choose. At which point should you find an equation of the linear approximation? And the book is not very clear about that, and for that reason I don't really like these questions. So if you look in the book from the questions of this section, if you look a bit up earlier questions, there they tell you which x0 value to pick. And here, well, you have to do that yourself. So you have to find suitable x values for which you know exactly the sine function, because here is being asked for the sine of 1.0. And then if you would look in the answers of the book, what they do the tangent line at pi over 3. Because pi over 3, pi is 3.14 over 3, that's approximately 1. So you could use the tangent line at pi over 3 to find an approximation of sine 1.0. And here the sine of 4 over 9, the book uses 2 times pi over 3. Apparently that's close to 4 over 9. So you have to find a point x0 that is close and for which you know the exact function values, and then you can use them. But as I said, if we would ask this in a test, we would most likely give you the x0 where you would have to find the linear approximation and not ask you yourself to find this x0 point. Okay. So that is the questions here for now. Irina had a question last week too about answers for the test questions that I sometimes put in the lecture. So sometimes in the lectures I have questions which I do not cover, but I tell you to try and solve on your own. For the slides of the past couple of weeks, I have added answers to those slides. So you can go back to those slides and I've added the answers there so you can check them. They're short answers, so you can see if you did it correctly. If you find that you had something different yourself and you don't see how you should do it, please let me know and I'll cover them in more detail. So also today I have a couple of these questions in there and you will see that I already put the answers there. So that brings us to the new theory for this week, and as I told you, it is integration. Now, we sometimes are a bit confusing maybe in the way that we cover the mathematics here. So sometimes we pretend that you didn't study any mathematics in high school yet and we start from scratch. And sometimes we say, well, you already did this in high school and now we build on top of that. So I'm going to talk about integration, assuming you didn't see it before, but of course the bits that you already know, I'm not going to cover them in much detail. But the most important message is everything you already know from integration, so that you have to look for a primitive function or an antiderivative of a function, that still holds. And if you already know how to do the integrals that we're going to ask you, that is fine, and you can use the high school mathematics that you already know. Now, before I start talking about integration, I'm going to look at two examples, two introductory examples, to hopefully convince you that this is an important topic. So let's see. Integration, as I already said, is kind of the opposite of differentiation, and we will see that. And actually that result that there's a very close relation between differentiation and integration. It is called the fundamental theorem of calculus. So you've just started studying at university, and we have quite recently started this calculus course, but today we will be talking about the fundamental theorem of calculus. So if you like, one of the most important theorems of calculus. And that is basically how we can evaluate, how we can compute, how we can find integrals. Now, first of all, a little bit of an outlook. So the sections that we will cover from the book by Smith and Minton are from chapters 4, so 4.1, 4.2 up to 4.5, and then a little bit from chapter 6. To start off, in a minute, I will talk a little bit about the income distribution of a nation's residents. So, as a Dutch student know for sure, and maybe if you came to Eindhoven to study at Eindhoven University, you have seen that in the Netherlands, on the third Tuesday in September, our government always presents the budget for the coming year. So they make the financial plans. And in those financial plans, one of the important things that is being considered every year is the income distribution. So how is the complete amount of money that is being earned in the Netherlands, how is that distributed over the people? And as an introductory example, I would like to show you how you can measure that and how you can basically catch that information in one number. And that one number is called the Gini coefficient. So that's going to be my introductory example. Also, when I talked about differentiation, I talked a little bit about traveling by train and the velocity. And if you measure how far you have traveled, how you can find the velocity. Because we now go from differentiation to integration, I will also revisit my train example a little bit. And maybe you recognize the train on the first slide. That is one of the first Shinkansen trains, the bullet train that people in Japan use. And the topics are basically area under a graph, integration techniques, and the fundamental theorem of calculus. So let's first look at this income distribution. So the way that is measured is you can make a plot where on the horizontal axis you put the population in a country and you put them in order from poor to rich. So here on the left are the poor people and here on the right are the rich people. So the amount of poor versus rich people. So the poorest people are on the left and the richest people are on the right. On the vertical axis we put the income, the total income in a country. So if everybody would earn the same amount of money, then we would have this red, basically y equals x graph. That means that everybody has the same income. Okay? Now, in reality, this is not true. And there is people who have a much higher income than other people have. And what's going to happen then is that you get something like this blue graph where poor people have a below average income and rich people have a much higher income. And the further this blue graph here is away from the red graph, the more uneven the income distribution is. So in the extreme case that there is only one person who gets all the money that is being earned in a country, you would have a flat line here. So it would go like this. And then on the very right, there is this one person and he gets everything. It jumps to 100%. And everything in between can happen, of course. Now, these types of graphs, you actually see them in the plans that our government makes. So in the budget that they make for the coming year. Now, it is not very convenient to have these pictures all the time. So it is easier if you're making plans and you want to say something about the income distribution, it is easier to catch this in a number, so to have one number describe this. So what you see here is a couple more of these pictures. And here on the left we have a pretty even income distribution. Here it gets more unequal, and here to the right you see that we have a very unequal income distribution. In the figures below, what happens is that this amount of money that you see here, that is kind of the income that people need to get by. So if you want to have a normal life, you want to have a roof, a bed, and something to eat every day, then you need this amount of money. And what you see here on the left, when the income distribution is quite even, you see that there is few people who are below this basic amount of money that everybody needs. And the more uneven, so the more you go to the right and the more uneven the income distribution gets, you see that there is a larger amount of people, and here it's almost the entire population, that are below this level. So basically they are too poor to lead a normal life and to have the first requirements that everybody needs in life. Now, to measure this, the way you can do that is invented by an Italian mathematician called Gini. And what he did is he said, well, if you have this curve here, what we are going to do is we're going to compute the area of the red region, that's A. We're going to compute the area of the blue region, which is B. And then we're going to compute A over A plus B. And then times 100% because percentages are easy to work with. So then if you would have a Gini coefficient of 0%, it means that you have the completely even income distribution where everybody has an equal income. If you have a Gini coefficient of 100%, it means that this fraction here equals 1, and it means that B equals 0. So it means that we have a completely uneven income distribution. So in order to compute these numbers, what we are going to be needing, and that is why I put this introductory example, is the area under a graph. And then back to the pictures, you see that indeed if we have a Gini coefficient of 30%, the income distribution is pretty equal. Here it is 60%, here it is 90%, and then it gets more and more unequal. And there is a few very, very rich people with a high income, and there's a large amount of poor people who have a low income. So that's the interpretation here. So the main message is that computing the area under a graph is something that you may need in applications. Okay? Now, that's one example. Let's do another one, because we will be talking about integration quite a bit, and I would like to convey to you the message that this is an important thing that we need. Now, before, when I talked a little bit about traveling by train, we made a graph where we put on the vertical axis distance traveled, on the horizontal axis time in hours, and we made a simple graph like this, S is S of t, where for instance you're traveling from Utrecht to Den Bosch, and in the beginning you're going quite slow, and then the train picks up speed and it goes quite slow again when it approaches Den Bosch. And we have seen how you could compute the velocity at a certain moment in time by computing the slope of the tangent line. So that's basically what we covered last week, talking about differentiation. Now, I would like to reverse the picture a little bit. So say that you're again in a train, and now we are traveling, say, by Shinkansen train, by bullet train from Tokyo to Kyoto, which is about 500 kilometers. And say that you have your mobile phone and you're going to register the speed of the train. Or in the Shinkansen, there is even a monitor that tells you the train is running with this speed at the moment. So then you could write down the velocity in kilometers per hour, say every 15 minutes. So every 15 minutes, you're going to look at the monitor and you're going to see the velocity and you're going to write down how many kilometers per hour the train is going. Now, if the train would be traveling with constant velocity, of course that's not very realistic, but if it would be, say that it's traveling with 200 kilometers per hour, and you have traveled for 1 hour, you're in Nagoya, then the distance after 1 hour is, of course, that's not a very difficult question, 200 kilometers. If you would have been traveling 2 hours, of course, 100 kilometers, and an additional 100 kilometers, so you have traveled 400. And if you travel for half an hour more, then you're in Kyoto, and you have traveled 500 kilometers. Now, if you look at the picture, of course, this is a very simple situation. But basically what we have done is we have taken here the velocity of 200 kilometers per hour, multiplied it with 1 hour and again with 1 hour and then with half an hour. And basically we have computed the area of the three rectangles you see. So here are three rectangles A, B and C. And basically we compute the area of these three rectangles and they tell us how far we traveled. So this is a strategy that you can also use if you're traveling with non-constant velocity. So here's a situation, maybe a tiny bit more realistic than the picture here on the left, where we are traveling. We start with velocity 0, then we pick up speed and we go to a maximum speed and then we slow down again. So if we would like to compute now how far we have traveled, say at this moment in time here, well, what we would have to do is compute the area of the shaded region here. And then we know how far we traveled. So the distance traveled is the area under the graph. Now how can we compute that? That's the next step. So now we know that apparently for some applications, either income distribution or maybe traveling and find the distance that you traveled, apparently sometimes it is important to find the area under a graph. Now how can we do that? Well, going back a little bit to the Shinkansen, and we're in the train and we're writing down how fast, with what velocity the train is currently going. So what you could do is say that you do that every half an hour, and then after half an hour you register in your little booklet this velocity, and then what you have traveled is approximately the area of the bar that you see here. So this bar that I'm shading now, the area of that rectangle, that is approximately the distance traveled. If you register it after 1 hour again, and you take then the area of this second rectangle and you add them together, then you know how far you have traveled. So the complete distance that you have traveled is approximately, so here it said this means is approximately equal. So how much we have traveled after 2.5 hours is approximately the velocity after half an hour plus the velocity after 1 hour, 1.5 hours, 2 hours, 2.5 hours, times the amount of time. So what we are doing is of A, B, C, D and the invisible rectangle E, of those 5 rectangles we compute the area, we add them together, and that is an approximation for the distance traveled. Okay? So that's nice. So now we know how to get an approximation to the distance that we have traveled. Or we can find an approximation more general if we have a general function y is f of x, how to compute the area under the graph. How can you make this better? Well, that's obvious, right? If you think about the traveling by train, do not do these measurements every half an hour, but for instance every 15 minutes, every 0.25, every quarter of an hour. And then you would get something like this. And from the picture here, you can already see that this is going to be a better approximation, right? Because here we have the exact quantity that we would like to compute. Here you see that this is an approximation, but kind of a rough approximation. This one gets better, and it probably won't come as a surprise to you that we're going to shrink the time interval, so the time between two measurements. We're going to let it shrink to 0. And then we are going to find the exact area. So for here, if you write down the velocity of the train every 15 minutes, what you would get is an approximation of the total distance traveled that is approximately equal to the velocity after 15 minutes plus the velocity after 30 minutes, 45 minutes, 1 hour, 1 hour and 15 minutes, and so on. Times, well, the time interval, 1/4 of an hour, 0.25. Yeah? Now, two more remarks on this slide. One is, this is kind of cumbersome to write. It's a lot of work, especially if you take even more time points or even smaller delta t. Then here we have 10 velocities that we need to add together. If you want it to be better, maybe you should take 100 velocities or 1,000 or 1,000,000. And then you don't want to write this plus, 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 plus all the time. You could use dots maybe to do that. But there is also a more mathematical notation. And that is if we introduce time points like this. So ti is a time point. So we have t1 equals 0.25, t2 equals 0.5, t3 equals 0.75, and so on up to t10, which is 2.5. And then this notation here, so the big sigma, so this is the Greek capital letter for S, called sigma. What it means is we are going to do a sum, so it's for summation, Greek letter S for sum, and I is going to run from 1 up to 10, so I is going to take on the values 1, 2, 3, 4 up to 10, and we're going to sum what it says here. So basically what it says here is precisely what it says up here, but it's a bit shorter notation, and it's also a notation that you can also write down easily for 1,000 or 1,000,000 terms. So it's just a way of writing that more conveniently. Nothing exotic going on here. So going away now from our train example, what we could do, oh well, this is still a train example, sorry, the next slide is more general. So this is still a train example, so we still have this sign-like shape. And here I already took more of these rectangles and they get smaller and smaller. The width is going to 0. So here it is a bit more general. So the time interval we're considering goes from 0 to 2.5 hours. We're going to cut that into n subintervals. So nothing exotic is going on here. This is just we have the time interval from 0 to 2.5 hours, and we're going to cut that into equal bits. The amount of intervals that we have is n, and that means that every time interval, so they all have the same distance here, and the distance that you have here is called delta t, and that is the total distance, which is 2.5 over the number of subintervals that you take. Okay? So that's what's happening here. So we have from 0 to 2.5, we take n subintervals, which means that every subinterval has this length, delta t. So I'm defining the time points here. So the time points, again, nothing special is going on. This is just labeling. So this is t1, t2, t3, up to here at the very end we have tn. And then the area under the graph can be approximated with what is in this box here. So we call that Sn, so that's the sum of the sum of those n bits, which is Vti times delta t. So basically it is the area of one of these rectangles that you have here. So if I take one of these very slim rectangles, then one of them has this area, and we're going to sum them all together, and that is the big sigma notation. Take all these rectangles, all these sub areas. Okay. So this is the main idea of what you're actually computing if you're doing integration. So we're going to introduce the integral in a second, but basically we are going to compute these types of sums where the number of terms here, so n is going to infinity, which means that at the same time this delta t will be going to 0. So this is really more general. Now we're going back. We have a function y is f of x. We consider that on an interval from a to b, and we would like to know what is the area under the graph. So we're going to assume here that f of x is larger or equals 0. So that means it's above the horizontal axis, and we're interested in the area between the graph and the horizontal axis. So let f be a function that is continuous, so it doesn't have jumps, it's not ugly, it's nice. And we're going to assume here that it's larger or equals 0. Then we're going to proceed in the same way as we did for the time travel, the train travel example. So we're going to cut it into n sub-intervals. I'm now going to give them length delta x, b minus a over n. So again, nothing special is going on here. We still have the interval from a to b. We're going to cut it in equal bits. There's going to be n of those sub-intervals. And now each of these have, if you take 2 points, or every sub-interval has length delta x. So that means that delta x is the total length b minus a over n. I am going to introduce the xi, so that's just the points that we picked. And then I'm going to approximate the area under the graph with this sum here. So the sum is now, we now have f of xi, because I labeled the horizontal axis x like we normally do, times delta x, and that is the distance between 2 points. And as you can see, and as we have seen for the train travel example, if you take more points, delta x gets smaller, the approximation gets better. And then the main idea is that if you now let n go to infinity, we talked about limits and we talked about what that means. So if you take the limit of n is going to infinity of these sums, that is the integral. So the area under the graph, this is basically the definition of area. So this is what area means if you're not talking about shapes where we know how to compute the area, like a rectangle, and for a circle or a triangle or square, we know how to do that. In general, if you have a funny shape like you see here, this is, mathematically speaking, the definition of area, but of course you already have an intuitive understanding of what an area means. Now, you could wonder, how do you choose, if you have such a little interval from here x1 to x2, where do you take the function value, and does it matter? So in the previous examples, I took the right endpoints. But if you like, you could also have taken the left endpoints. So here I'm going to evaluate the function at these points. So I'm going to approximate the area with this quantity, which is a little bit different from this one, as you see. Because here I have f of xy, right grid points, right endpoints of the intervals, and here the left ones. And if you like, you could also do the middle ones. Now, you can probably imagine that if you let the number of intervals go to infinity, the size shrinks to 0, that it doesn't matter. Because these little subintervals, their width will shrink to 0, and then it doesn't matter which of these points you take. I have already told you before that my normal line of business within mathematics is numerical mathematics. In numerical mathematics, if you want to find numerical approximations of an integral, a very complicated integral, you would use these types of tricks. And then you normally have a preference for this situation. And you can probably tell from the pictures why that holds true. This approximation is the best one because you have a little compensation or above and below the graph within an interval. So if you look, for instance, here, you see that the area of the red bar here is a little bit too much, here is a little bit too little, and that kind of compensates out. So that's not important, but if you use this approximation for an integral, it's called the midpoint rule, and it's a well-known method in numerical mathematics. You will find it in Wikipedia, but that's beside the point because we are going to do exact integration here. So The claim is now that if you do this, so if you have an area, you're going to approximate it with a sum like the ones we have seen before, but now I have written here Ci, and this Ci is in the interval from xi minus 1 to xi. So it can be the left point, it can be the right point, it can be the midpoint, it can be any other point. If you take a sum like this, for some choice of Ci's, it is called a Riemann sum. And if the limit here, so this limit of the approximation, if you can let n go to infinity, and you find that it goes to some value, for every choice of the point Ci, so whether you take the left points, the right points, the midpoint, another point, if you always can do that, always find the same value, then we call the function integrable. So it means we can integrate the function. That is what integrable means. And mathematically it means what it says here, that this limit exists. And then we define the integral as the limit. Okay? So this seems very complicated, and it seems that you would have to have very special functions f for them to be integrable. That is not true. So integrable is kind of a weak property. Every nice function that you know, so without jumps and without singularities and stuff like that, tangent can be complicated, logarithm can be complicated if you're close to zero, stuff like that. But if you have a nice, well-behaving function, sine, cosine, polynomials, rationals, if you stay away from where the denominator gets zero, those types of functions, they're all integrable. And in fact, if you have a continuous function, so continuous, you can draw it without lifting your pen from the paper, then it's integrable. So continuity is a stronger property than integrable. So there is a bunch of functions that you can integrate. So before we go how you can actually compute integrals, let me do a special example. So we have now, up till now, basically seen which problem we're trying to solve, finding an area under a graph. The notation for it, because the notation is basically what you see here, this sign. What it means, but not really how to compute it yet. So we will be doing that, and that's what you already know from high school mathematics. So you're going to look for a primitive function and then swap in the endpoints of the integral, this a and b, the stuff that you already know. But before I do that, sometimes you don't have to do all these computations, and you can immediately find an integral by actually looking what you're trying to compute. And there's a couple of questions on that, both in the book and also in the online questions, so in the practice questions and also in the weekly questions that you get. And I would like to give an example there. So you could, for instance, have this question from the online questions. So evaluate the integral from 9 till 12, square root blah 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 dx, by interpreting the integral as an area. And this by interpreting the integral as an area, that is a kind of code word or a phrasing that means do not try to compute it, but look what it actually says. So you can probably imagine that this one is quite hard to do if you would like to find an antiderivative, a primitive function. That's going to be a bit tough here. So let's see what this actually means. And that's basically what's being asked here. So if you call the integrand, if you call that y, and then if you compute y squared, you get rid of the square root sign. And if you then rewrite it a little bit, you find this equation here. And that equation, hopefully you recognize what that means. That is a circle. So I also have a picture here. It is a circle with center 9, 0, x equals 9, y equals 0. The radius is the square root of 9 is 3. So you have a circle with center x equals 9, y equals 0. And then the radius equals 3. So it goes through the horizontal axis at 6 and at 12. and this here would be plus 3, and this here would be minus 3. So that is the circle that you have. Now, if you look what is being asked here, so we integrate from 9 till 12. So we integrate over this bit on the horizontal axis, and then we're integrating along what it says here, the square roots. So we're integrating the top bit of the circle, and then only from x equals 9 up to x equals 12. So what we have is that the integral is 1/4 of the area of the full circle. Now, the full circle, you know that the area is pi times the radius squared, so there's 9 pi. We only have 1/4 of that, so apparently the integral is 9 times pi over 4. So without doing any looking for primitive functions, just by looking at what are we actually trying to compute, by trying to interpret it geometrically, you can find what the value is of this integral. So the code word here is interpret the integral as an area. If you see that, then make a picture. Try to understand what it looks like and what we're actually trying to compute there. Now, before we go to actually finding integrals, actually computing them, let's first look at what happens if your function is not positive. So before I had the assumption that f of x is larger equal 0, but here you see that we have something that is below the horizontal axis. Now, if you look at the definition, so this is what we wrote down for the definition, then you see that in the definition it is nowhere necessary or required that f is a positive function. So it allows for the function to be negative, and indeed, basically what you have is that the integral over the whole interval is the integral from a to c, so that's this bit here, and that is non-negative, that's positive, plus the integral from c to b. And if you look at the sum here, because your f is less or equal 0, you will find that this whole thing is less or equal 0. So you can also integrate functions that are below the horizontal axis, but then the area gets a minus sign. Okay. Now, one thing more, a few properties, and they follow directly if you look at the definition for integral in terms of a sum, where n is going to infinity, then you will immediately see that if you're trying to integrate f plus g, then you can integrate f, and you can also integrate g and then add them together. You already know how to do this, so I'm going through this pretty quickly. If you multiply a function with a constant, you can also move the constant in front of the integral. If you integrate from a to b and c is some intermediate point, you can integrate from a to c and then from c to b. If you have the integral from a to a, you will find that it equals 0 because, well, you're integrating from one point to the same point. If you swap the limits, you get a minus sign. And you also have that if f of x is less or equal g of x, then the integral is also less or equal the integral. And that also follows directly from the sum definition. Now, one thing more before we move to finding antiderivatives. Using integrals, you can talk about the average value of a function. So if we have a function like this, and for instance, you could think that you have a tank of water and that you have a wave there going in one direction and you would like to know the average height. So if you just leave your tank and then let the water settle down again, which level does it take? So what is the average value of the function? Now, you could approximate that by picking points in this interval, say x1 up to xn, and then sum those function values and average them. So take 1 over n times the sum of those function values. That would be an approximation of the average. But how should you pick those points and how many of them? The more you take, probably the better the approximation is going to get, right? So in general, what you could do, you could take them at the same distance. So for instance, like this. And then you could take x1, x2 up to xn minus 1, and this one is then going to be xn, so b equals xn. So I'm going to take them all the same distance. Distance between two of these points is called delta x, and the points themselves are a plus I times delta x. I equals 0 gives a, I equals n gives b, and then everything in between. And then this here, so this approximation to the average, you can rewrite that because delta x equals b minus a over n. So n times delta x equals b minus a. The total length of the interval b minus a is the same as n times delta x, all these sub bits. So n is apparently b minus a over delta x, and 1 over n equals delta x over b minus a. And now if you plug that in, if I replace this 1 over n with delta x over b minus a, then you have this approximation here. And then last step, what you can do is let n go to infinity, and then hopefully, or if you look back later on, because this is all going quite fast, I realize that this will go to an integral. So what we find, if your function is integrable, you could take the limit of n going to infinity, find an integral, and apparently the average of a function can be computed as an integral like this. So it's 1 over the interval length and then the integral of the function. So this is a good point to have a little break because it's 2:15. So I'm going to stop talking for 15 minutes, leave you a bit of peace. If you have any questions, drop them in the chat box from YouTube. And I'll see you again in 15 minutes. So we continue at 2:30. So welcome back after the break. I see that in the live chat, Jana asks for solutions to the homework questions corresponding to the fifth edition of the book. I don't know offhand, but I'm going to find out. So I'll get back to that on Wednesday and try to find them for you. Okay, so let's go back to the slides then. Before the break, we were talking about the average value of a function, and we have derived the formula you see here in the blue box. So apparently, if you want to know the average value, you can use an integral for that. And I have added also a slide to give a little bit more interpretation background to what that means. So you can think of an average height. And here in the picture, I have added the area under the graph. So the area under the graph is the integral, and that is the area of the red shaded region that you see here. Now, if you look at the definition of average that we have derived from the previous slide, then basically what that means is that the rectangle that you see here in the right picture, so the rectangle that has here length b minus a, and here height f average, that has the same area. So the red region here on the left and here on the right, they have the same area. So that's another way to look at this average height and what it means. So again, if you have a tank of water and it has a wavy pattern on that, usually that's in 3 spatial dimensions, of course, but if you would like to make a crosscut, if it stops moving the water, then this is the level that you will get. Now, a lot of talking about integration already, and probably if I would have asked you before the lecture, what do you think of when I talk about integration, you would have started thinking about primitive functions or antiderivatives, as they're also called. And of course, that is the way that we will compute integrals if we can do so exactly. So there is a close relation between differentiation and integration. And the main idea is that we will be needing antiderivatives. So if you have a function little f, then we call capital F an antiderivative or primitive function if when you differentiate capital F, you get little f. So another name is primitive function, and you know that they're not unique. So if both f and g are antiderivatives, then f is g plus a constant. Because if you differentiate them, then here you get f prime equals g prime is apparently little f if they are both primitive functions of little f. And then there is a notation for that, so we write the integral fx dx. So there is no a and b here, we just leave out the limits. If we do not write limits, then we mean an antiderivative or a primitive function. So the integral fx dx, that is capital F plus a constant, because we can always add a constant there. So if we ask for a primitive function, you should write plus the constant there. Okay. Now, knowing this, then we immediately know a lot of antiderivatives by looking at differentiation rules. So here are a bunch of differentiation rules that we have already seen or that you already have seen in high school. If you differentiate x to the power n, you get n times x to the power n minus 1. If you reverse that, you have an integration rule. So the integration rule can be written if you would like to find a primitive function of x to the power n. You take x to the power n plus 1, but you have to compensate for the n plus 1 if you differentiate, so divided by n plus 1 plus a constant. And n should be unequal to minus 1, otherwise we have division by 0. So what happens for this situation if n equals minus 1? Well, basically that's 1 over x. And from this differentiation rule, we have that a primitive function for 1 over x is the ln, and you can write here the absolute value. So that's not immediately clear, but this is convenient, and it will be helpful if you write absolute value instead of just ln x, because then the limits of your integral can also be negative numbers, and otherwise they cannot be. Then from the derivative of sine is cosine follows that the primitive function of the cosine is sine plus a constant. And then we also have for the sine function, from the differentiation rule for the tangent, it follows that 1 over cosine squared has tangent as a primitive function. From the differentiation for arctangent, we have that the integral of 1 over 1 plus x squared dx is the arctangent function. The exponential function is easy to differentiate and to integrate. And then finally, there is one for the arcsine. There is also one for the arc cosine, but arc sine and arc cosine, if you look at the derivative, there is just a minus sign, so that's why it's not in the list. And as you have already seen, this list here is what you will get during the exam. So with the exam, you have a formula sheet, and on the formula sheet are these types of integration rules. The precise form you know from the midterm, you will also get one of those at the final exam. So, the fundamental theorem of calculus. The fundamental theorem links differentiation and integration together, and it basically tells that they cancel each other. So there's two versions, and I labeled them here FTC, so Fundamental Theorem of Calculus Part 1, and there's also going to be a Part 2. Part 1 is basically what you already know from high school and have already used to compute integrals. So if you have a continuous function, if you can find an antiderivative, if you can find a primitive function, then the integral from a to b little fx dx is, and then this notation means that you get a primitive function and you evaluate it between the two endpoints. So this is just a short notation for f at b minus f of a. So this is the version that you already know. Then there is a part 2, and part 2 is a little bit similar. We start with little f, which is continuous, and now we're going to define this integral, and then f prime equals little f. This one is a bit more obscure at the moment. I'm going to cover a number of examples, and hopefully once you have seen the examples, you know what it means and how to read it. But if I already run ahead a little bit, it says here f prime. So that is the derivative, say d dx of fx. So we find that the d dx of the integral from a to x f t dt is apparently, according to the theorem, little f of x. So how should you read this? Well, basically, if I have a function little f, and I first integrate and then differentiate, I get my function back. So if you start somewhere and then integrate, differentiate, the integrate and differentiate kill each other. So that's how you should read this theorem, and how you can make use of that. That will become clear in the problems when we go to solve them. But this is more or less the interpretation. So what you see here on the left is if you want to compute an integral, you have to find an antiderivative. And what you find here on the right is if you differentiate an integral, then they just cancel out. So that's kind of the gut feeling you should have of what these theorems mean. Now, how you actually use them, that's far more important. The first one, just what you did in high school to evaluate integrals. So here is the same thing again, the same FTC part 1. So basically the fundamental theorem of calculus, although it probably wasn't named that way when you were in high school. And what it tells you is that if you would like to find an integral like this, you have to look for an antiderivative of what it says here. So this bit here we will call fx, and then we will start looking for capital F, which is an antiderivative. So how do we do that? Well, this here, f of x, is x to the power 1/2 minus x to the power minus 2. And now we can use the table where we can find primitive functions for that. And you know that a primitive function for x to the power 1/2 is x to the power 3/2, but we have to compensate with 2/3. And the primitive for x to the power -2 is x to the power -1. And we have to evaluate that in between 4 and 1. And maybe that's a bit unclear for me, but this notation here, sometimes I also write this f of x in between b and a. And what I will also do sometimes is f of x, and then write x is b, x equals a, and this is also the same as f of x, x equals b, x equals a. This is just notation. There is nothing special going on here, but sometimes we use this vertical line like you see here. Sometimes we use the square brackets like you see here. Sometimes we just write the limits, and sometimes we want to be extra clear and we write x equals b, x equals a, because in a bit we will be doing substitutions, going to different variables, and then it makes sense to make super clear that we're working with x here, and x takes on these values. So that's just different notations. You can use whichever one you like. All of them are correct. I use both of them because they're both common, and I always try to be very consistent, but here is something that it's a bit of a taste what you use, and I like both here. So this notation means that here, this primitive function, we have to evaluate it at 4 and then subtract what it is at 1. So plug in those values. So this is what it equals for x equals 4 minus the values for x equals 1. And then if you compute that, you find 47/12 apparently. So that is how you compute integrals, simple integrals that you can simply look up in the table, or that you can immediately see a primitive function for. Okay. Another example, the integral from 0 to 4 e to the power minus 2x dx. You can immediately find a primitive function it's an exponential, so you take the same exponential. If you would differentiate with the chain rule, you would get an additional -2, so we have to compensate for that with this -1/2. And then you substitute the limits, and you find that apparently this here is the value of the integral. This is all stuff that you already know, so I'm just going through them to show you that this FTC1, as we labeled it here, is nothing new. This is how you have been doing integrals all your life. Next one, integral from -3 to -1, 2/x dx. Now, if you think a little bit about that, what that means, so we have the function 2/x, so what does that look like? If x equals 1, this function equals 2. Yeah. And if x is going to 0 from the left, this goes to plus infinity, so it's something like this. If x is going to infinity, it's going to 0. And here it is going like this, right? It is symmetric. So this is the function y equals 2/x. And now we have to integrate it. Let's make this a little bit longer here. We have to integrate from, say, -3 to -1. So what we are interested in here is the area -3 to -1, 2/x dx. So we are trying to compute the red area you see here. Okay. Now, a primitive function for 2/x is 2 times the natural logarithm, 2 times ln x. But what you see is that the limits of this integral are negative. So this is why if you are looking for a primitive function, you should use the ln of the absolute value of x. And that's also in the table of integrals that you will get during the exam. So 2 times ln absolute value of x. And then in between -1 and -3. So don't forget this absolute value, as it says in red here. And then you just plug in those values, and because of the absolute value, you have no problem, and you find that this apparently is -2 times ln 3, which is a negative number, and that's correct, right? Because your graph is below the horizontal axis, so you should find something negative, so that's good. Now, so far, this is mostly stuff that you've already seen before, and now we get to a bit that is probably new to you, which is how can we use this FTC part 2, so the fundamental theorem of calculus part 2, which basically tells you that differentiation, we take f prime here, of the integral, because there is capital F here, they basically cancel out. So let me write that once more. We already had before, but basically differentiation, so d dx of the integral from a to x f t dt equals f x. Now, if I cheat a little bit, then you could say, well, that makes sense, because what you're doing is the d dx of the integral a to x f t dt, and let's write brackets here. Now, let us assume that we can find a primitive function, okay? So then we have, this is the d dx of, and here we wrote capital F, so that's a primitive now. Let's also make that t, sorry about that, f t in between t equals x, t equals a. So that is the d dx of f x minus f a. Oh, let's write normal brackets here. And if I differentiate capital F of x, capital F is a primitive of little f. So this equals f of x minus 0, because capital F of a is a constant. So this is f of x. So maybe you find this confusing because I'm just using abstract formula and you don't know what they mean yet. So I am going to do examples, but first I want to kind of get you used to the idea that differentiation and integration, they cancel out. So let's see. So one way you can read this is that every continuous function, because I'm going to start with little f being continuous here, so every continuous function little f has an antiderivative. So there is an antiderivative, capital F, which is this integral. We know that little f is continuous, so we can integrate it. It's integrable. We have seen that before. And now apparently there is an antiderivative. And the other one is what I've been trying to tell you already a couple of times. Differentiation and integration cancel. So a very simple example that is not very terribly interesting. If you have an expression like this, well, here, this thing here is f of t. So f of t is t squared minus 2t plus 3. And then it says the d dx of the integral of little f t dt. Well, that is precisely what the theorem tells us about. Because it tells us that then if we differentiate that we find little f of x. So without doing any computations, I can immediately write here this expression, which is just little f of x. So this is straightforward using the theorem. The reason I wrote this down, so this is immediately what the theorem tells you, but here we can check it. because you can check by first finding the integral. So we can do the integration and find capital F of x. So that's the integral from 1 to x of this expression. We can find a primitive function here, plug in x and 1, and we find apparently that this here is capital F of x. So we have done this here, and we have found that we have this expression for capital F of x. Next we can differentiate, so I can compute f prime of x, and if you do that you find x squared minus 2x plus 3. So indeed you find the same thing. So that gives a little bit of confidence in this formula and what it tries to tell us. Now, the nice thing is that you can use these types of results to find integrals for much more complicated functions. So first, this one is still relatively simple. So here we're being asked to find the d dx of an integral. Well, we can immediately use the theorem. So we can immediately say, well, define capital F of x to be the integral. Then apparently what FTC2 tells us is that f prime x is the integral cosine t difficult. So we have the integral from 2 to x squared cosine t dt. And we cannot directly use FTC2 because FTC2, that only works if there is an x in the upper limit. And now there is not x, but there is x squared. However, there is a reason that I put these two examples next to each other on this slide. You may think that this thing is somehow related to this integral, and that's true. So let's see how that works. So I'm going to define now capital G of x because we already used f of x and it's still on this slide. And I would like to differentiate this thing, but I cannot directly use FTC2 because there is this x squared here. Now, if you compare the two examples, particularly if you compare this fx to this gx, then you see that we have that gx is f of x squared. Okay? So that means that if I need to differentiate, I can also differentiate what it says here. And if I differentiate what it says here, I find f prime at x squared, and then with the chain rule an additional 2x. And then I plug in f prime x squared, that's cosine x squared. And then I'm done. Then I have found the primitive. So that's how you can do that if you have something more complicated in the top or in the bottom limit. For the examples on this slide, I could still have performed the integration first, right? Now let's look at a little bit more difficult example. So here we're being asked for the d dx of, well, the integral limits depend on x again, and here we have to integrate this thing. And this thing, it is not immediately obvious what is going to be a primitive function here. It is not so easy to integrate, to find an antiderivative. So, but here we can also use the FTC2 theorem. So how can we do that? Well, we cannot directly use it because we could only directly use it if we would have something of the form integral from a to x, but we have the integral from 2x to x squared. Now, in the previous example, I already showed you that we can kind of get rid of this x squared by using a trick. We can do something similar here. So I will be using FTC2, so that works for this one. So I have to do some rewriting here. So how can we do that? Well, what I'm going to do is rewrite the integral. So first of all, I have the integral from 2x to x squared. I write it as the integral from 2x to 0 and then from 0 to x squared. The 0 is arbitrary. You could have picked 10, 5, 100, whatever you like. As long as this function is defined, well, that's defined everywhere. Because if you take some constant there, basically it drops out because it appears twice here. And once with a minus sign if you like. Next, this first integral, I can swap the integration order, but then I get a minus sign. And then I'm already quite close to the form that FTC2 works for. Constant to x. Well, not really x, there is a 2x and there is an x squared, but hopefully these two are related to this thing from 0 to x. And for this thing, I can directly use FTC2 because I know that if I differentiate it, the differentiation and the integration cancel, and I get this, the square root of x squared plus 1. Now, if I want to differentiate this thing and I want to differentiate this thing, they are again related to this function capital F. So let's wrap it up and let's put all the ingredients together. So what you can do is say, well, basically the integral that is originally being asked, so with these limits, I can write that as this thing plus this thing, which I can now write using this capital F function. If I differentiate capital F of 2x, then I find the f prime of 2x, and with the chain rule an additional 2. So f prime of 2x, and then with the chain rule an additional 2. And if I differentiate this thing, I find f prime at x squared, and with the chain rule an additional 2x. And now I can just plug in that f prime equals the square root of x squared plus 1. And if you do that, you see that f prime of 2x gives a 4x squared plus 1. And the f prime of x squared gives here an x to the power 4. And this is the derivative that was being asked. Now, I can imagine that this is a lot of formula work and a lot of algebra. And what is most important here is to keep track of the plan. What are you actually trying to compute? Which steps do you need to take? And then you will find this not so difficult. So the main idea is that if you have something integral from a constant to x, and then whatever ft dt, so if you have, like here, if you have something of a constant to x ft dt, and that's called f of x, that then if you differentiate, you get f of x. So in a sense, this is quite powerful because this ft here, that pops up here again, that can be a horribly difficult function that you cannot integrate. It can be the sine of the cosine of x squared. Good luck finding a primitive function there. You're not going to manage. But apparently we don't need to. Because we first integrate and then differentiate again, we don't have to find an antiderivative, but we can use the function, basically the integrand here itself. So that is the main idea, and then there can be a little bit of complications where you have that the lower limit depends on x. Well, you just split it, you go to a constant, and this is not precisely x, these things, but then with the chain rule, you can still get it to work. So those are the main ingredients for these types of questions. Okay, so that's great. That wraps up the first bit of the material for this week. And if you think about it, you haven't seen that much new stuff as compared to what you have done in high school. So we talked about integration, where you can use it, and where the definition of the integral comes from and what it means. It's the area under the graph. This FTC fundamental theorem of calculus part 2 is probably new to you. And the rest of this week's material is concerned with integration techniques. And there are two basic integration techniques that we will cover. One is called integration by substitution, and the other one is called integration by parts. Now, differentiation is something that most students find not too difficult, also conceptually what's going on there. And if I give you some function, then probably you feel confident how you can compute the derivative, how you can differentiate it. If you need to integrate it, that gets more difficult and is almost a kind of an art form, because you have to see, well, maybe I should use this technique, and then you also have to make choices in there. And this is very well captured by the following cartoon here. So I'll let you read it first and then I'll talk about it. So basically what you see here is that if you do differentiation, well, try applying, and there is not a whole bunch of different things that you can choose from. There is chain rule, power rule, quotient rule, product rule. You've seen all of them. And then you can see if you're done and yes or no, and you keep repeating that. It is quite straightforward, not too difficult, and if you think a little bit about it, if you can do any programming, you could probably write a computer program for this. That's not very difficult to capture. If you do integration, well, you can try applying integration by parts, substitution, so we will be talking about these techniques. And then if you're done, well, you're happy, but you see that all kinds of things can appear with Cauchy's formula, partial fractions, Riemann integration. We talked about that. Riccio algorithm, I don't even know what that is. Install Mathematica, that's always a good idea. Stokes theorem, what the heck is a Bessel function? Phone call to mathematicians, you're welcome. Burn the evidence. So integration is a lot more messy, a lot more can go on, and basically it is not as clear cut and straightforward as differentiation is. Nevertheless, let's look. The top bit here, so basically if we cut off here, this is still reasonable, and we will talking about these two things. And we will start with substitution. So with substitution, we will be able to solve many more integrals. And there are numerical techniques to find integrals, but if you can find an exact answer, that is always preferable. So as long as you can do integration exactly, and there's much computer software to help you with that, but the basic techniques, it's important that you manage them, because a very simple integral, you should understand yourself that you can actually find it, that an exact solution may exist. And B, if you use computer software, you may want to check your results, because a computer happily may give you an answer, but whether it always holds true, that is not clear. So, for instance, the software that this cartoon talks about, Mathematica, that's great software. It's also the software that is used to run Wolfram Alpha, if you know that software. It is great software, but it can also give you completely wrong results, and you should be very careful with every result that a computer program gives to you. So that's also one of the reasons that we talk about that stuff here. Substitution. So let's see. The first example, I'm first going to do a couple of examples to convey the idea to you. And then hopefully I can sketch the general idea, the general method, and you can do other problems yourself. So here we are being asked for an antiderivative of 2x e to the power x squared. Probably you could manage to do so. So how you could approach this is that you say, well, this looks pretty horrible. But I do recognize here that there is an exponential function here, e to the power x squared. But if you do the ddx of e to the power x squared, so you might try to pick that as a primitive function, because an exponential, if you differentiate it, you get the same exponential, and then there is the chain rule and you get maybe extra bits, but this would be a nice start. And you see that, well, if you differentiate, you get e to the power x squared, because it's an exponential times 2x. And a small miracle has appeared, because apparently the 2x here that precisely helps you with the chain rule. So what you see is that apparently the original question here was carefully crafted so that you could pick this thing as a primitive function. Now here, maybe you can see that, especially if you've done a number of these problems, and of course you should try to do that because that's the only way you learn mathematics, by actually doing it and trying to solve problems yourself. So then you get a certain skill here, and it goes better and better. But there is a more structured way to do this. And the more structured way is like this. We are going to introduce a new variable. So we're going to introduce a variable u, which is going to be equal to x squared. So it's basically a function of x, u equals x squared. The reasoning behind it is that we have an integral that involves an e to the power x squared. And then with this new variable, it's going to be e to the power u. And if I am going to integrate that with respect to u, then I get e to the power u, and that's very simple. So that's a bit of the reasoning behind it. Now, I would like to write this whole integral in terms of the new variable u rather than x. Now, there is a dx here, so how do I get rid of the dx? How can I write dx in terms of du? Now, the idea is the following. So, u is a function of x, so u prime of x, which is du dx, we have seen that notation before, equals 2x. Just differentiate x squared and you get 2x. And now, this bit here, du dx equals 2x, I rewrite that to du equals 2x dx. So if you find me cheating here, if you think, well, can you do that? Because this here is not really quotient, is it? It's not du divided by dx, but it's like one notation. So yes, that feels like cheating. Let's say that you can do that. So we have du is 2x dx. So what that means is that the 2x dx that I have here, I can replace that with du. So writing the whole integral in terms of u, I now have that this e to the power x squared is the same as e to the power u. I have that 2x dx is du. And now let's forget about everything we've seen so far. We are being asked to do this, to find a primitive function for e to the power u du. Well, that's trivial. That's just e to the power u. So we can solve it. We find as a primitive function e to the power u plus a constant. Now, our original question was in terms of x. So let's substitute back u equals x squared. So I'm going to express the result in x again. So I'm going to replace u with x squared. And then we have e to the power x squared plus c. So that is how substitution works. Let's do one more example. Find f of x, capital F of x, is the integral x to the power 3 plus 5 to the power 100 times 3x squared dx. From a bit of a abstract point of view, you could say, well, this here is just a polynomial. It's a pretty big polynomial because here is x to the power 3 and then to the power 100. So that's going to be a very high power of x and then times x squared. So if we would expand the brackets, just substitute out, we would get hundreds and hundreds of terms. But still, it would be a polynomial, and for a polynomial, we can easily find a primitive function. So in principle, we can do this, but not by hand, at least not in this way. So we have to do it a bit different. So let's do substitution. So what I'm going to do, I'm going to introduce a new variable u, and it's going to be x to the power 3 plus 5. If I do that, then this x to the power 3 plus 5 to the power 100 becomes u to the power 100, and I can integrate that because the primitive for that is u to the power 101 over 101. Okay. How to choose this u? That is the key ingredient in using substitution. If you do many examples yourself, you will get handy in that. So you will see how to do it, and I will give you some guidelines, but still you should try and practice this because at an exam you'll have to make that choice yourself. So if you do that, so now I'm giving you that this is apparently a suitable choice, then u prime or du dx is 3x squared. So we find that du is 3x squared dx, and a little miracle, this wasn't the original integral. So if we now write the original integral in terms of u, then the first factor becomes u to the power 100. 3x squared dx is apparently the same as du. Forget everything that happened so far, just look at this thing that we need to find. Well, it's easy to find a primitive function there. So a primitive function is u to the power 101 over 101 plus a constant. And now we substitute the original definition for u back. U is x to the power 3 plus 5. So apparently the answer to the original question is this thing. And indeed, that's nice about integration. If you differentiate it, you find the original question back. So if you would differentiate this expression, you see that indeed we find what it says here. So with integration, you have a great tool to check your answer. So you should always do that. One more example of integration by substitution. So I am going to solve this thing, and as you see, this, if you don't know about substitution and you would just be asked to find this integral here, so to find the primitive function, that's hopeless, right? You're never going to manage here. But if you make the choice u equals 3 tangent x plus 4, then this thing here becomes u to the power 5. And hopefully this bit here is going to help you with the du, how to get to du. So what is du? Well, differentiate. Du dx is 3 over cosine squared, because if you differentiate this, you get 3 over cosine squared. So apparently du is 3 over cosine squared dx. Now you see there is a 3 here, which is not here. There is a 1 here. So somehow we have to get that in. So what you can do is multiply the whole thing with 1 over 3 times 3. Then you move the 3 up there. The 1 over 3 you just write in front of the integral, and then you're basically done. So let's do that. So I write it as 1 over 3 times the integral, and this becomes u to the power 5 du. Again, forget everything that happened so far. Just look at this integral. Well, that's easy peasy. It's u to the power 6 over 6 plus a constant. So we do that. So we find 1 over 3 times u to the power 6 over 6 plus a constant. If you multiply that out, you get 1 over 18 u to the power 6 plus c over 3. The constant is not important, so you could call this c tilde a new constant. And I advise you to do that. So if you have something like this, some complicated expression that is just a constant, give a new name. Because, well, the value is not important, we're not going to use it anyway. So just call that c tilde, c hat, d, e, f, whatever your favorite letter. And then we're done, right? So now results, we substitute u, the definition, back. And apparently the answer to the original question was 1 over 18, and then in between brackets 3 tangent x plus 4 to the power 6 plus a constant. So that's how to do integration by substitution. Last example, and then we're done for today. Here something interesting is going to happen. So again, we have now an integral, and we have a square root of a square root in the denominator. So that is pretty hopeless. Let's try substitution. So I'm going to do u is 1 plus the square root of x, because then this whole thing becomes 1 over square root of u. And 1 over square root of u, that's u to the power minus 1/2. I have a primitive function for that. But if you compute du dx, you find 1 over 2 times square root of x. And now something strange happens because, well, it's not in there yet. So du is 1 over 2 square root of x dx, but there is no 1 over square root of x in the original integral here. Now, how can you do that? Well, if you look here, we have u is 1 plus square root of x. So u minus 1 is square root of x. So 1 over 2 times square root of x is the same as 1 over 2 times u minus 1. And that is the idea here. So try to write that also in u. So what do we have then? So this is what I just did. So du can now be written like this, which means that dx is 2 times u minus 1 du. And now we can write the whole integral in terms of u and do the integration. So you see that this is a bit more involved. We need more work here for this example. So if I express the integral in u, this bit here becomes 1 over square root of u. That's great, that's just as it worked before. For dx, we now have a more complicated expression, 2 times u minus 1 du. So 2 times u minus 1 du. And then we have this thing. So this is the original integral, but then in terms of u. And as I said before, forget everything that happened. Just look at this integral, and this is not a very difficult one. So this we can easily solve because we can write these separately, and then we have u to the power 1/2 and u to the power minus 1/2. We can find primitive functions for that, and then we substitute x back, and then we have found the answer to the original question. Maybe a bit fast, look at it more slowly and check and try to solve a couple of these questions. If you have questions, you want me to show stuff on Wednesday, get back to things, I'll happily do that. For now, let's just see what we have done. So we have looked at integration by substitution. The way it works is you have to choose somehow a function u of x. Then you have to compute u prime, and you have to use du is u prime x dx. You rewrite the integral, you express it in u, you solve it, and you substitute u back. And the way you choose it, a few guidelines. That's the difficult part. How should you choose your substitution? So if you have an integrand, so the function you want to integrate, that's called the integrand. If it is some function, say sine, cosine, exponential, square root of something difficult, then that's something difficult. So whatever is in the sine or in the square root, whatever you try to take the square root of, that's what you should try as a substitution. And then you have to recognize u prime somehow and then integrate. So this is a great moment to stop for me at this moment in time. So today we have done substitution. We will probably go back there on Wednesday, depending on your questions. We will also see a different integration technique on Wednesday, integration by parts. You may have seen that in high school already. And we will talk a little bit about the special type of integrals with sines and cosines that are relevant for many practical applications. So this is where I would like to stop for today. Thanks for being here. Let me know all the questions that you have. I will happily address them. I hope the midterm results will be available by Wednesday. And I'm going to stop here, and I hope to see you again on Wednesday morning. Thanks and bye.